Hi, good morning. Today we are going to discuss a few methods by which we can solve a system of linear equations. So, by the time a system of linear equations, what we mean is uh, an equations of the form like a11x1 plus a12x2 plus etc. a1 nxn is equal to b1 a1 21x1 plus a22x2 plus etc. a2nxn is equal to b2, and in such a way that it continues up to a m1x1 plus a m2x2 plus etc. a mn a m n xn is equal to bn. So here we have n unknowns, namely x1, x2, x3, etc., xn, and m equations, in n unknowns. And this one can be written in a matrix form ax is equal to b, where capital A is the coefficient matrix a11, a12, a13, etc., a1n, a21, a22, etc., a2n, am1, am2, etc., amn. That's the coefficient matrix. A is the coefficient matrix. X is the vector, the column vector, which contains the terms like x1, x2, etc., x1, x2, etc., xn. This x, and b is again another column vector b1, b2, etc., bn, the column vector of constants. So that's the general form of system of linear equations. Ax is equal to b, where a is the coefficient matrix, b is the column vector of constants, and x is the column vector of unknowns. So this is known as uh, the system of linear equations. Now, in previous classes, maybe in plus 2 classes or in first year classes, you have already discussed about some methods by which we can solve uh, this kind of system of linear equations. By the time solve, what we mean is find the value of the column vector or the unknowns x1, x2, etc., xn, which satisfy the uh, system of linear equations. Now, there are different possibilities. The system may have a unique solution, it may have infinite number of solutions, or it may have no solutions at all. There are three different possibilities. Anyway, we are familiar with a few methods by which we can solve such a system of linear methods. So here we just list down a few methods which are familiar to you. One is Cramer's rule, which is based on the concept of determinants, and you may have gone across, or you may have you are familiar with the Cramer's rule, which as part of your plus 2 curriculum. It's a method based on the determinants, and therefore it is only useful when there are uh, n unknowns and n equations, and n independent equations actually. The second method is uh, by reducing the system of equation or the matrix into raw equivalent canonical form. So by doing some raw calculations, we can reduce it into uh, the canonical form, and then we can solve the system of equations in a simple way. So this is also familiar to you. It's part of your maybe first year curriculum or second year curriculum. So I'm not going to discuss the method of reducing into Croatian and canonical form. I'm going to assume that this method is familiar to you. And the third one is a straightforward method. The value of x can be calculated as x inverse into, so just take note, x is inverse into x. It is x is equal to a inverse into b. That's another method by which we can calculate the solution. But this is also possible only when the matrix A is a square matrix, which is also an invertible matrix, or A inverse can be calculated. Now, the matrix AB is again familiar to you. The matrix AB is known as the augmented matrix, and we do the raw equivalent raw calculations in this augmented matrix while we using this the method of reducing to raw equivalent canonical form. So the matrix AB is known as augmented matrix. So they are the basic these preliminary facts which we are assumed. And now in this chapter or in this session, we are going to illustrate two concepts. One is Gauss elimination method, and the second one is Gauss Seidel iteration method. So first we illustrate the concept of Gauss elimination method. So here we have a system of linear equation, three equations in three unknowns. So this one can be written as in a matrix form. Ax is equal to b as a is equal to 1 1 minus 1 uh, 8 6 so 6 is set. So coefficient of x is 0 here. So it is 0, coefficient of y is 8, coefficient of z is 6, and x is minus 2, y is 4, z is minus 6, that's the value of a. Then x is x, y is z. Then the constant matrix b equal to 9 minus 6, 40. So that's the equivalent matrix representation of the equation Ax is equal to b. Now how we can solve this system of equations using Gauss elimination method. So first step, we write down the augmented matrix, which is given by AB is equal to, first we write the values of A, which is 1 1 minus 1, then 0 8 6 minus 2 4 minus 6. Then the values of b, that's the constant times, which are 9 minus 6 40. Now in Gauss elimination method, we reduce the matrix augmented matrix AB into a upper triangular matrix by using raw calculations. By the time raw calculations, uh, what we mean is we can interchange the rows or multiply a row with a non-zero scalar quantity or non-zero real number, and the third kind of operation is add a scalar multiple of a row to another row. So we can multiply the second row with the non-zero constant and add it to the first row. That's all. That is possible. So these three kinds of operations are going to be used to reduce the augmented matrix into an upper triangular system. Now, by the time upper triangular system, what we mean is the values on and above the diagonal is non-zero, and all the values below the main diagonal is 0. So here we have to reduce, we have to make the values in positions here, here, and here are equal to 0. So that is how we uh, transform it into an upper triangular matrix. So here we are going to use some row calculations. The first leading element here, 1, is a non-zero value and it is 1. So we can keep it as it is. So we don't have to change the first row. In the second row, again, the leading value or the value under this 1 is 0. And therefore, again, we don't need to change any value in our second row. And the third row, the value is minus 2, let make it 0. So for that, the value of R3 is replaced with R3 plus 2 into R1. So we do a row calculation in such a way that all the values under the leading element here become equal to 0. So R3 gives R3 plus 2R1, and all the other values remains as a constant. So we get an equivalent matrix, not equal, it is equivalent, uh, 1, 1, minus 1, 9, no change in the first row and no change in the second row. So 0, 8, 6, minus 6. And here we make a row transformation in such a way that this value become equal to 0, and that is R3 plus 2 into R1. So minus 2 plus 2 into, so this calculation, minus 2 plus 2 into 1. So that is equal to 0. The same type of calculation is going to done in our remaining elements. So the 4 plus 2 into 1, that is 6. Then minus 6 plus 2 into minus 1. So it is minus 6 plus minus 2, that is minus 8. And the constant time, it is 40 plus 2 into 9. 2 into 9 is 18. 40 plus 18, 58. So that is the equivalent form. Now, while reducing into row equivalent canonical form, the next step is to make the leading element 1, that is this position as 1, the term 8, the term in the position of 8 is divided by 8, or the second row is divided by 8, and using the leading row we make all the other elements here 1 and 6 equal to 0. That is the process. But in our case, in our Gauss elimination method, the next process, we kept the first row as it is, so 1, 1, minus 1, 9, and the second row, the leading, just consider the leading element, and it's a non-zero value, so we keep the term there itself. So it is 0, 8, 6, minus 6. Then we make the element below 8, that is 6, equal to 0, or we do a row calculation in such a way that the 6 become equal to 0. So for that, the time R3 is given by R3 minus R2 by 8 into 6, or we can write it as R3 minus, here it is for 3 by 4, 3 by 4 R2. So this is a simplified notation. You can use any one of these notations which is easy to calculate. So anyway, the first term is 0, second term is 0 because we make the row calculation in such a way that this term become equal to 0. You can just recheck the value here so that whether your row calculation is right or wrong. But anyhow, the value below the leading element is always equal to 0. And here uh, the value is given by R3, that is minus 8 minus 3 by 4 into R2, that is 6. That's equal to, we can simplify it. Um, is minus 8 minus 9 by 2. 9 by 2 is 4.5, so it is 8 plus, so it is 16 plus 9 divided by 2. If we take 2 as the LCM, then it is minus of 16 plus 9 divided by 2, that is 25 by 2 negative. So it is minus 25 divided by 2. And now at this position the value is R3 is 58, the value is 58 minus 3 by 4 into R2, that is minus 6, so it becomes plus 6. This 4 and 3 get cancelled, denominator we have 3, here is 3, and what we have is 58 plus 9 by 2, that's equal to 58 into 2, that is 6 uh, 1 1 6 plus 9 divided by 2, that is 125 divided by 2. So here the value is 125 divided by 2. Now that's a matrix which we obtained by row calculations, and we rewrite the given system of equations using the equivalent matrix. That is what we have is uh, this matrix here, the equivalent form of A. It is 1 1 minus 1 0 8 6 0 0 minus 25 by 2 into x1 sorry xy z is equal to, the constant matrix has an equivalent matrix or row as 9 minus 6 125 divided by 2. So that's a equivalent matrix, and we can rewrite it as a system of equation as x plus y minus z is equal to 9, 8y plus 6z is equal to minus 6, and minus 25 by 2 z is equal to 125 divided by 2. Now by this kind of row transformation we obtain a system of equations which can be easily solved. So look at this system of linear equations now. The last equation can be solved very easily, and it gives, so here from this equation z is equal to 125 divided by 25, there's a minus n also, so it is 5 minus 5. Now let it be equation number 2. Now if we substitute the value of z is equal to minus 5 in equation number 2, what we get is 8y is equal to minus 6 minus 6 into minus 5, which is equal to minus 6 plus 30, that's equal to uh, 24. So y is equal to 24 by 8 is equal to 3. And now if you substitute the values of x and y in our equation number 1, which is x plus y minus z is equal to 9, this is our equation number 3. If you substitute the values of z and y, which already have in our equation number 3, which contains all the three variables, x plus y minus z is equal to 9, or x is equal to 9 minus y plus z is equal to 9 minus 3 plus minus z. That's equal to 9 minus 3 minus 5 is equal to 9 minus 8 is equal to 1. So here we get the solution. The solution x is equal to x is equal to 1, y is equal to 3, and z is equal to minus 5. So this is our required solution. And this particular method is known as Gauss elimination method. So that's a method by which we can solve a system of linear equations using Gauss elimination method. And remember, this is not an iterative process. This is an algebraic method, and the next method which we are going to use is an iteration method. Iteration methods are used when solution by algebraic method is either too difficult or uh, it is not possible. But in our case, we are just illustrating the iterative method using a numerical example. And this particular problem can be solved using, say, Gauss elimination method, or by reducing into equivalent form. All those methods are possible in this particular case. But uh, what we are going to do is illustrating the concept of Gauss elimination, Gauss Seidel iteration method, and the practical significance of Gauss Seidel iteration method is is when we get a system of linear equation which uh, is difficult to solve using the traditional methods, the algebraic methods. So anyway, here we have a system of linear equations, which again is a system of equation in three unknowns, and we have three equations. Now, the first step, we rewrite the given system of equations uh, in the following way. The first equation is rewritten as x is equal to 1 by 8 into 8 minus y minus z. Then the second equation is rewritten as y equal to 1 by 4 into 4 minus 2x minus z. And from the third equation, we can have z is equal to 1 by 5 into 5 minus x minus 3. So this is a simple method. We rewrite the first equation in the form x is equal to something. The second equation is rewritten in the form y is equal to something. And the third equation is rewritten in the form z is equal to something. The only thing which we may observe is that while rewriting the equations, if say, for example, if we consider the first equation, we rewrite it as x is equal to something, and here we have a property. Consider the coefficient of x, it is 8. The coefficient of y and z are 1. For the, if you take the modulus, absolute values of coefficient of y and z are 1, then 1 plus 1 is less than 8. And in the second case, the, the equation is rewritten in the form y equal to, and the coefficient of y is 4. The modulus of other two variables, modulus of coefficients of other two variables are 2 and 1 respectively, and their sum is less than 4. And this particular property should be satisfied by the equations. If a particular equation does not satisfy this condition, then we can overcome that difficulty by just rewriting or just shuffling the order of equation 1, 2 and 3. So if in the first equation, say if we consider the first equation and if we trying to rewrite it as say z is equal to 8 minus 8x minus y, that kind of transformation is possible, but there is a problem. The coefficient of z is 1. The sum of coefficients of coefficients of other two variables, that is x and y, is 9, and this 9 is greater than 1, and we cannot choose the equations in this manner. So this is invalid. If we choose in that way, the numerical method is not going to converge. That's the problem. Anyhow, here we get 3 equations. Now we start with a trial solution, say x0 is equal to 0, y0 equal to 0, and z0 equal to 0. That's a trial solution. We just denote it as superscript. This superscript is used because in conventional methods, usually the variables are denoted as x1, x2, x3, etc. And in the first iteration, the values of x1 are x10, x20, x30, and so on. So there is already a subscript, and if you use subscript of subscript, the representation becomes too confusing, and that is why we are using the superfix to denote the iteration steps. So this is our first iteration step. X naught is equal to 0, y naught is equal to 0, and z naught is equal to 0. Now we substitute these values in our equation, and we get the values of x, y, and z in our first iteration. X1, sorry, it is x superfix. X1 is equal to, if we substitute the values in the first equation, it is 8 by 8, that is 1. Y1 is equal to, from the second equation, if we substitute 0, 0, it is 4 by 4, that is again 1. Then Z1 is, from the third equation, it is 5 by 5 is equal to 1. Now we can use this set of equation, x1 is equal to 1, y1 is equal to 1, and z1 is equal to 1 in the same set of equations 1, 2, and 3, and find the values of x, y, and z in our next iteration. So that's a method by which we can use Gauss Seidel iteration method, but we have a more rapidly convergent method in which we calculate the value of y1 by using x1 is equal to 1. So if you use x1 is equal to 1, then the value of y1 is equal to 1 by 5 into 1 by 5 into, sorry, 1 by 4 into this 1 by 4. For the time being, it is concentrate on the value of 5. 1 by 4 into, we use the latest value of x and the available value of z. So it is 1 by 4 into 4 minus 2 into 1 minus z is 0. So this is equal to 4 minus 2 is 2. 2 by 4 is 1 by 2, that is 0.5. Then we calculate the value of z1. z1 is calculated using the latest available values of x and y. That is 1 by 5 into 5 minus x is equal to 1 and y is equal to 0.5. So it is 3 into 0.5 is equal to 1 by 5 into 5 minus 1 minus 1.5, it is 2.5. So it is 2.5 by 5, that is again 0.5. So that is our second iteration. So by using the latest available values of variables, we can make the system, make the iteration process converge in a faster phase. Now, to calculate the value of x2, the second iteration, the value of x2 is calculated the latest available value of x, y and z. So it is 1 by 8 into 8 minus y into, that is y, the latest value is 0.5 minus x3, the latest value of x3 is also 0.5. So it is 8 minus 1, 7 by 8. 7 by 8. 7 by 8 is 0.875. 0.875. And now the value of y in the second iteration can be calculated as 1 by 4 into 4 minus 2 into the value of x1, that is 0.875, then minus x3 or z, okay, x and z value, the latest available value of z is in the previous iteration, which is 0.5. So it is 0.5, and this is equal to, just by simplifying, the value is 0.4375. Now the value of z in our second iteration is given by 1 by 5 into 5 minus y, sorry, 5 minus x is equal to 0.875, that's the latest value, 0.875 minus 3 times y, the latest value is 0.4375. You always use the latest value, which make the convergence faster. So this is equal to, the value is 0.5625. Now that's the end of second iteration step. Then in our third iteration step, the value of x in the third iteration step is given by 1 by 8 into 8 minus y, that is 0.4375 minus z, 0.5625, and the value is 0.875. So the value of x remains unchanged. Okay, anyway, let us calculate the value of y also. Y in the third iteration is 1 by 4 into 4 minus 2 into the value of x, that is 0.875, which is the latest value of x, minus the value of y. Y, not y, it is z, value of z. Value of z is 0.5625, 0.5625, and that will give the value of y as 0.4219. So there is a change from the change in the value of y from the previous step. And now the value of z. Z3 is given by 1 by 5 into 5 minus y, that is 0.875, minus y, 3 into y, 3 into the latest value of y, that is 0.4219. And this will give the value of z as the third iteration 0.572. There is also a small change in the value of z. Now again we are going to recalculate the values of x, y and z in our fourth iteration. So third iteration is over here. Now in the fourth iteration step, the value of x, the value of x in our fourth iteration is the value of x in our fourth iteration is 1 by 8 into 8 minus 8 minus y. Y the value is 0.4219 minus z, that is 0.572. So the value of x is obtained as 0.876. The value is rounded to 3 decimal places, and anyway this value is different from the value obtained in our previous iteration. And the value of y in the fourth iteration is 1 by 4 into 4 minus 2 into 0.876, latest value of x, minus the value of z, that is 0.572, is equal to by 4. In the fourth iteration the value is 0.419. The previous step is 4219, here this 0.419, so there is a small change. And the value of z in the fourth iteration is 1 by 5 into 5 minus 0.876 minus 3 into the value of y, which is 0.419. The value is obtained as 0.5734. Now all the values are different from the values obtained in our previous step, and therefore we have to go to the next iteration step. So x5 is equal to 1 by 8 into 8 minus 0.419, the value of y, minus value of z 0.5734. All these values are rounded to 3 decimal or 4 decimal places. It is rounded to 4 decimal places, and here the value is 0.876, and the value of y in the fifth iteration is equal to 1 by 4 into 4 minus 2 times 0.876 minus um, the value of Z, that is 0.5734, which is equal to 0.419. So far the values of X and value of Y are the same. These two values are the same, and these values are the same. And if we calculate the value of Z, in the fifth iteration, the value is 1 by 5 into 5 minus uh, X, that is 0.876, minus 3 into Y, that is 419, 0.419, and it is 0.5734. 5734 is same as that obtained here. So these two values are the same. So we get the same set of values in fourth and fifth iterations, and therefore we can stop the iteration process here, and the values or the final solution is given by x is equal to 0.876, y is equal to 0.419, and z is equal to 0.5734. So that's a required solution to the system of given system of linear equations. So this is an iteration method, and you have to fix the required number of accuracy level in the first step itself, and we stop the iteration process when we get the same set of equations in same set of solutions in two consecutive or two successive iteration process. So these are the two different methods to solve a system of linear equations. So for the time being, this is enough, and I recommend you to go through a number of problems to become familiar with the raw calculations, and to become familiar with the iteration process. So thank you.